All right, ladies and gentlemen, welcome back for another round. This is Mr. Doolin. I thank you so much for tuning in. Today what we're going to do is we're going to take a look at ionic bonds. So ionic bonds result from a net attraction between oppositely charged ions, right? And in ionic solids, they form a crystal lattice structure of these closely packed ions such that the attractive forces are maximized between the ions and the repulsive forces are minimized. So what we have to do is we have to go back to a previous lecture where we discussed this potential energy versus distance graph. So recall that in your head really quick. And we have to look at when two atoms approach each other for these bonding purposes, what happens if the electronegativity values between the elements are not the same? Because what we looked at in covalent bonding, the electronegativity values were similar to each other. Well, what happens if there's a significant difference? And that's what we're going to address today. So when we get these elements that approach each other, we know we get some overlap between the electron clouds. And what tends to happen when there is a large difference in electronegativity values is that the relatively low electronegative element will lose electrons, and those electrons will be transferred to the element that's bonding that has a relatively high electronegativity value, right? Now, I know most people, when they memorized at first what ionic bonds was, or what they are, is they memorized, oh, well, an ionic bond occurs between metals and nonmetals. And so we see on the screen here, and this is how would you generally, most of the time people would have just said, oh, well, your ionic bond is a bond between a metal and a nonmetal. Well, what we need to do is we need to understand why that's a general rule, right? Or why that generally happens the way that it does. So we mentioned before that as these as these elements approach each other, the one with the relatively low electronegativity value will lose electrons, and the element with the relatively high electronegativity value will gain said electrons. And so you'll see, and think back to your periodic table, right? Electronegativity is based on those Coulombic attractive forces within an atom. So we know that metals on the left side of the periodic table all have relatively low electronegativity values compared to those elements on the right side of the periodic table, which is where my nonmetals are found. And so it's the same definition, but we have to understand the meaning behind what it means to be a metal, right? Metals generally have relatively low electronegativity values, and nonmetals have relatively high. So what this causes is my metals, they are generally going to lose those valence electrons, and my nonmetals will gain them. In losing the valence electrons, my metals are going to form my positive ions, and in gaining the electrons, my nonmetals are going to form negative ions. Well, what you'll see me refer to these as is this will be your cation, and your nonmetals will be your anions. And I want to reinforce just the large understanding piece here, that the piece that I need you to put together into your puzzle is why this occurs, and it really goes back to the fact that I've got a large difference in electronegativity values here, and so that's what causes the transfer of electrons, and then why metals generally lose electrons and why nonmetals generally gain electrons. And so what I've got shown on the screen here now is actually referred to as a formula unit, right? And a formula unit is just the simplest ratio of cations and anions in an ionic bond, right? And we understand that according to Coulomb's law, opposites attract. So my positive is attracted to my negative. And what happens when these form solids is we'll just see a regular repeating arrangement where I'll form positives around every negative, right? And then my negatives will arrange themselves in such a way that they will balance in between. And so what we see, and we mentioned it earlier, is that they'll pack together in these solids to maximize attractive forces and minimize the repulsive. So what we'll see is my positive negative will try to align next to each other, and my positive positive or negative negative will try to distance themselves as far away from each other as they can occur. Right? And the solid that we're forming here, this is actually called a crystal lattice, and the term crystal just means that it's going to be regular and repeating. And so we'll see this because of the arrangement of the positives and negatives to maximize attractive forces, minimize repulsive, is that we get this just repeating arrangement of these ions in the solid. Now, we need to also go back and understand, and I guess relate back to intermolecular forces here. And this is where we get a fuzzy line between breaking a bond versus breaking an intermolecular force. And the ionic bonding in ionic solids is where this occurs. And it's something called lattice energy, right? We understand lattice energy from a previous unit is the energy required to separate these ions and dissociate them, if you will. And so we understand now that if we're looking at this, we have to kind of ask the question, well, am I breaking a bond or am I breaking an intermolecular force? And the answer is just yes. There's a fuzzy line. It's not distinct. It's not yes or no. It's not one or the other. It's kind of a combination of both, because if I'm going to dissociate ions out of an ionic solid, I can be, if I'm going to call this my formula unit here, that I would say, hey, if I separated these, that would be my breaking in a bond. But the reality is, well, how do I know if that's my formula unit, or if this is my formula unit, or if this is my formula unit? Because there's lots of different ways to combine those simplest ratio of ions. And so we're kind of breaking all of it as we separate these ions out of this ionic solid. And so it just goes back again. I want to relate and make sure that we understand and remember from lattice energy. Lattice energy is based on Coulombic law, right, or Coulomb's law and Coulombic attraction, that my force of attraction is proportional to charge over radius squared. And so we need to take a look and make sure that we understand what makes this lattice energy higher, right, is how I'm going to get you to learn this. And the charge of the ions is actually what this is. The Q value is your charge of your ions. Your R value here is actually now ionic radius, right, rather than energy shell like we've seen back in a previous unit. So this is ionic radius, and the Q value is my charge of an ion. So we need to understand, based on the way that this equation is written, that if I get a larger charge of an ion, I'll actually get a greater attractive force, which means my lattice energy will be higher. If I get a smaller atomic or ionic radius, then my Coulombic attractive force would be a higher force. So we understand that based on Coulomb's law, lattice energy, higher attraction if my charges of my ions are higher and my radius of my ions is lower, is what's going to cause that increase in lattice energy. And so that's it, ladies and gentlemen. I know that was quick and fast, but that's a summary of ionic bonds. If you have questions, hopefully you have those written down. I'll see you in tutorials for those. Otherwise, I will see you in class.